So before attempting this lesson and worksheet, you should have completed the Pascal's triangle activity where you work through those 4 different worksheets and then tied it all together and looked at overall sort of the patterns that you were seeing as a result of Pascal's triangle in each of those applications. And so one of the things that comes out of the Pascal's triangle is the relationship to the binomial expansion. Whenever we're multiplying a binomial times a binomial, or a binomial, to the exponent 2, or a binomial to the exponent 3, there's a pattern that we can use thanks to the Pascal's triangle that lets us take a shortcut and find all the coefficients and all the exponents on the variables, so we don't have to actually do the distributive property multiple times over and then add all of our like terms together. When we do it that way, we have a lot more chance of making a mistake with a sign or with a computation error, or even just forgetting a term when you're collecting like terms at the end. And so this is much more efficient and much more accurate in terms of using that method. And so what we've learned through Pascal's triangle, remember the pattern is 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, etc. What we have learned is that those are the coefficients of the expansion of the simplest type of binomial, which is just one variable plus the other variable, both with coefficients of 1. And so in this case, if we are putting anything to the exponent 0, of course it's equal to 1. If it's just to the exponent of 1, it's just what we had inside the brackets. It doesn't actually start coming into play until we do higher exponents like squared and cubed and so on. So if we look at squared, the pattern is 1, 2, 1 for the exponents, just like the second row of Pascal's triangle, because remember the first row is row 0, then row 1, row 2, etc. And so if we move that up to cubing a binomial, which is usually a lot of work, now we know that the base coefficients are 1, 3, 3, 1, just like they are in the triangle for the third row of the triangle. Now, if that was to change and it was like 2a plus b cubed, and we'll look at an example or two like that in a minute, then your coefficients are going to be multiplied by whatever this term cubed is, and so on. So that's going to change those numbers, but those are sort of your base numbers that you're always going to multiply by. And then, of course, 1, 4, 6, 4, 1 is the next row of the triangle, and that's why we see these coefficients in these places here. Now let's look at the variables, because the variables are also following a pattern. If we think about the first variable, the one in the first position in our binomial bracket, then we start by taking the square root of that variable, and then we go down 1 exponent or 1 degree, and we're at a to the 1. And then we go down 1 more exponent if you want to look at it that way, and we would have a to the 0, which of course we don't write because that's just equal to 1. And if you look at the second variable, let's start at the other end of our expansion. We have the same pattern, but just going the other way. So we have b squared, and then b to the 1, which is 1 degree less than b squared. And then, of course, we could write in b to the 0, but we don't need to because that's just equal to 1. So we see that same pattern even as we get into higher and higher exponents of our expansion. So for cubed, we're looking at a cubed, a squared, a, and then a to the 0. And if we do the b and we go the other direction, we have b cubed, b squared, b to the 1, b to the 0. And so that makes it really, really easy to just go through and fill in all of those variables with the appropriate exponents. And again, if I gave you a binomial that was like a squared plus b cubed or something like that, of course that's going to square or multiply by a factor of 2 all of the exponents in our expansion. And we'll look at an example like that on the next slide. Sorry, not the next slide, the next to one slide. This is, in a nutshell, just pointing out another property that you would have looked at when you did the activity. And so we've got our Pascal's triangle worked out all the way down to row 7 here. So this would represent sort of an a plus b or an x plus y to the exponent 7 expansion. And you notice that we have 2, 4, 6, 8 terms in the expansion when the exponent is 7. So we always have one more term than the exponent. And so it may seem sort of silly for me to say find the middle term in the expansion when we've got an even exponent, and you think, well, if the exponent is 8, how can we have a middle? But there's actually 9 terms in the expansion of a plus b to the 8, which means that the fifth term will be our middle term. Over here, we have the Pascal's triangle again, but it's written a little bit differently, and this is the beauty of mathematics. I love teaching this topic because so many connections and seeming coincidences come together in such a beautiful way in this topic. We've talked about the choose notation, and we can write it like this, or we could write it as 0, choose 0. Or the other way we can write it is C 0, 0. All of those things mean choosing R things from N. So N choose R is the button on your calculator. And so we just have this written in N choose R form here in order to show you that the values we're getting in Pascal's triangle are also the choose values. And so these are really combinations. How many ways can you choose 0 things from 1? How many things can you choose 1 thing from 1? How many ways can you choose 0 things from 2, 1 thing from 2, 2 things from 2, and so on? And the values that you get when you work out those combinations are also the same values as the rows of Pascal's triangle, and I think that's just amazing, and it just blows my mind every time I think about this and sort of these beautiful connections that we see in math. And so when you're working out your chooses, this makes it easier again, because if you're working on, say, a probability problem that involves combinations or combinatorics, as we call this branch of math, then you don't necessarily have to go for your calculator and put in the N choose R each time. You could simply think about the Pascal's triangle or have it there in front of you and just grab the combination values as you need them. So there's another shortcut that we can make use of that's going to make things much quicker. And you'll find in university that, when you have timed tests in university or time quizzes, then if you have little strategies like this that you can use to calculate things quicker, then it gives you lots more time to sort of slow down and think through the problems that are a little bit harder and require a little bit more time. So finally, here's the examples that we were talking about. And so the first thing we're going to do is we're going to just expand a straightforward, simple, basic a plus b to the exponent 6. And let's look at how easy this is going to be. We're going to just go backwards for a minute and have a look. Well, why don't I just sort of write out our Pascal's triangle so we have it here on the same page. Oh dear, I'm going to run out of space. Okay, I'll just kind of move it over here a little bit. So we have row 0, row 1, 2, 3, 4, 5, and we need row 6, don't we? So we have 1, 6, 15, 20, 15, 6, and 1. So those are our coefficients that we're going to use in the expansion. And so that's pretty easy. We can just go here and we can write 1, 6, 15, 20, 15, 6, and 1. And then we're going to look at our variables. Our variables are a and b. And so we know, because this is a positive, we know that our signs are going to be positive all the way through. If it's a negative, what's going to happen is it's going to alternate plus, minus, plus, minus, plus, minus, like that. I'll show you in the next example. So we're going to start with a to the 6. And then we know that the degree of our a base is going to go down each time. And so we're just going to progressively write in smaller and smaller exponents as we go down. And we should run out by the end, and we're not going to write a to the 0 because that's just 1. Then we're going to start at the other end, and we're going to write in the b exponents starting with b to the 6. And then we're going to progressively reduce that exponent by 1 as we move to the left. And we won't write b to the 0. The last thing we have to do is just go through and put a plus between all of these guys. And that's the expansion of a plus b to the 6. One step, one line, and you got your final answer. It's not always that easy. Sometimes you have to do another step to sort of work out the final coefficients, and I'll show you how that works in the next example. So let's switch colors to keep this a little bit more organized, and we're now going to look at b, which is only an expansion to the exponent 5. So we're going to move up to the 5th row of Pascal's triangle. I'm going to do exactly the same thing as I did in A. I'm going to start by writing out my coefficients, and I'm going to leave a bunch of space in between so I can squeeze the other stuff in later. So let's make it nice and big like that. So now when it comes to putting in the values for my variables, my first variable was 2x, and this is where it gets a little bit tricky, because if the exponent's going to be 5, then the base is 2x to the 5. We're going to go back and take a look at that in the next step. So here I have a base of 2x to the exponent 4, 2x to the exponent 3, 2x to the exponent 2, 2x, and nothing because 2x to the 0 is 1. Now I'm going to do the same thing, only I've got a minus 3 as my second term. So I'm going to start at the other end with minus 3 to the exponent 5. And now I'm going to have minus 3 to the 4, minus 3 to the 3, minus 3 squared, and minus 3 to the 1, or just minus 3. All right. So the signs are going to come out in the wash, as I like to say, which means when we actually evaluate these bases and exponents, we're going to get a negative or a positive, and then you're going to see a pattern that you can use to always check to make sure that you got the signs right when you have the binomial in the form like a minus b. So let's go back and expand and simplify. The first term, we have 2x to the 5 times 1. So 2 to the 5 is 32. And x to the 5 is x to the 5, and if we times that by 1, we just get 32. So in the next term for our expansion, we have 5 times 2x to the 4, so that's going to be 5 times 2 to the 4, which is 16, x to the 4, and minus 3 to the 1 is minus 3. For the next term, we had 10. We're multiplying that by 2x to the exponent 3. 2 to the exponent 3 is 8, and then x to the exponent 3. And now minus 3 to the exponent 2, if we're squaring a negative, always turns out to be a positive, so that's positive 9. Let's keep going. We have 10 times 2 squared, which is 4, times x squared, and then we have negative 3 to the exponent 3, which is negative 27. Now we have 5 times 2x, and then negative 3 to the 4 is positive 81. You might need a calculator on some of those. I've just been doing this a really long time, so I can do them in my head. And then 1 times negative 3 to the 5 is just going to be negative 243. Okay. So now we're going to be able to write this expression with our signs in the middle, because we can see 5 times negative 3 times 16, 5 times 16 times minus 3, negative 240, x to the 4. Go ahead and use a calculator if you need to. And you see how we got a negative, so we know that the first sign is a negative sign. Now we have 10 times 9 times 8, that's 720, and that's positive x cubed. And then we have 10 times negative 27 times 4, that's negative 810 x squared. And so we're going negative, positive, negative, and they're always going to alternate, okay? We know the next one's going to be a positive, and 5 times 2 times 81 is another 810 times, oh, I did the wrong one, I'm sorry. We already did that one. Okay, or did we? No, I just forgot the squared. There's the squared, I did write it, I just didn't see it. Okay, the next one is going to be positive 810 x, and then I'm going to get negative 243 at the end. So here's my exponents, 5, 4, 3, 2, 1, 0, and all of the coefficients are different than the row of the Pascal's triangle because we had that 2 as part of our variable base, and so that 2 and the negative 3 to the exponents are going to multiply by the original coefficients and give us bigger numbers this time. But again, look what we did. We only needed 3 rows of work, only 3 lines of steps to expand something to the exponent 5, which would have been a nightmare if we tried to multiply a binomial times a binomial 5 different times in order to get that, and then try to group up all the like terms and hope that we got them all right and hope that we got all the signs right. All right, I included this question because it is similar to one that you're going to be asked to do on the worksheet. And so an expression in its simplest form for x minus y to the exponent 5. So what we want to do is keep in mind what we were looking at just a minute ago in terms of the choose or the combinations being what generates the numbers in our Pascal's triangle. Okay, and that's just the first few rows. Let's keep going and get the 5th row if that's, we know that the 5th row would be 5 to choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, gonna run out of space here, there we go, and 5 choose 5. And that's going to generate the 6 coefficients for this expansion. And so in simplest terms, our n is 5 and our r is the bottom number. And so in simplest terms, we could write that as 5 choose r. So whatever term in the expression we're trying to get, that's going to be the coefficient from Pascal's triangle that we're going to multiply in. And then we also know that our x variable, the first one in our binomial bracket, is going to start at 5 and then be 4, 3, 2, 1, 0. And so if it starts at 5, as we're going down, we're always subtracting the number for the position in the expansion that we're in. And that the other variable, sorry, that's an r, the other variable, in this case minus y, is just the opposite of that, or the complement of that. So it's just the r value. And so our general term would be 5 choose r, x to the 5 minus r, negative y to the r. If we tried that, let's do the expansion of the third term. And so we would be doing r choose 2, or 5 choose 2, sorry, x to the 5 minus 2, which would be 3, and minus y to the 2. And remember, these exponents always have to add back up to the 5 at the end. Okay, so our last example for today, we're going to break this lesson into 2 parts. The last example is where we're going to expand something to the exponent 5 for the binomial. And so again, if we think about Pascal's triangle, it really doesn't take long to write it out. all the way down to the fifth row. So we have 1, 2, 3, 4, and 5. Oops, that should be a 10, sorry. So there's our coefficients. And because x squared and minus 1 both have the coefficient of 1, then those coefficients are actually going to be the coefficients of our term. But we want the third term. And so this would be the coefficient of the first term, second term, third term. So we know we're going to start with 10. And then if we're on our third term, we're going to have x squared, and that's going to be to the 5 minus 2. And so it's going to be, let's make that a little bit neater here, sorry. Okay, so that's x squared. And for the third term, remember we're going to start with the exponent 5, the next one will be 4, the next one would be 3. And the second variable in this case is just a constant, it's minus 1, and so it would have to be to the exponent 2, so that 3 and 2 always add up to this 5 that we started with. And so if we simplify this a little bit, we have 10, and then an exponent to another exponent, you multiply those, so that's x to the 6, and then negative 1 squared is just positive 1, so that's just 10 times 1, x to the 6. Okay, in the worksheet that I have posted, only questions 2, 7, 9, and 10a are related to what we just looked at in those examples. So if you could please complete those questions before moving on to the next lesson.